All right, so in this problem, we are being asked to find just the output voltage. We're given an input voltage, right? So we can, in fact, calculate the output voltage and the current flowing up here, I naught. Right? The best way to approach most op-amp problems is to just, well, there's always the opportunity to look and see, is this one of the configurations that I recognize, right? If it is, that can help us to simplify. But then other than that, you typically want to approach it with, my favorite is to just do nodal analysis. I find that to be the easiest way to go, all right? So, in this circuit, can we recognize the configuration of the op-amp? Yes, we can. Typically, we want to look at what's going on with the feedback path into the negative or the inverting terminal, right? And so in this case, we have a feedback path that is going to tie our output back to our input, right? And this is a follower configuration, right? So whatever the input voltage is at the non-inverting terminal is the voltage that's going to come out at the output. That's pretty simple to see, in fact, because what are the golden rules of op-amps? The two input terminals are the same, and no current flows into them. Well, since this is a short circuit between V out and V in at the minus terminal, that has to be V0, and so that has to be V0, right? So we know that. So that's now one of our unknowns, right? It's at that point. The other unknown in this case is going to be that node right there. All right, so let's just call that V1. So now I have two nodes that I don't know the voltage of. If I can write down two equations, I can solve them. Right? So that's what I'm going to do. Kcl. So again, it's sometimes helpful to go ahead and prep your system by saying, okay, what are the directions of current flow? Well, since this is a positive voltage, I'm going to assume current flows that direction. And then otherwise, current likes to flow down to ground, right? Current will flow through here, but not into this branch, right? No current flows through here. And so then where's the other current going to flow? Well, we want the current flowing out this way. So let's just say it's flowing that direction, right? And now I've labeled the direction of current flow through each of my branches, right? Through each element. And I can proceed to write down my Kcl equations. So let's do Kcl at V1.
So much easier than number 11. They actually gave you the voltage for this one.
They did, that's right. In number 11, you had an unknown Vs right here. So now for number 12, you know this voltage, so there's one less step of unknowns to solve for. That's right. All right, so Kcl at V1, Kcl says currents in equal currents out. That's right. So current in is just this one, and the currents out are these two. Right. So current in, 20 phase of 30 degrees, minus V1. Right. Current always flows from the tail of the arrow to the head of the arrow, and then we divide by the impedance, negative J 8K. Equal currents out, so that's V1 to V0 divided by the 20 kilo ohm resistor. And then our final current out is V1 to V0, because we do know that that is V0, even though it's a different point in our circuit, divided by 10K. Okay. Now I can clean this all up, get my unknowns on the left and my knowns or constants, if you will, on the right. Again, with these ones, once you start dealing with imaginary numbers, they're in the denominator and everything, I prefer to let MATLAB do it. So I'll just write it down in a form sort of simpler, but not completely simplified, right? Like for one, there's a kilo ohm on the bottom of every one of these, so we know that that's going to cancel, right, if we multiply everything by 1,000. But other than that, I'm just going to kind of group things together. So I'm just going to pull everything to the left, everything else, all the constants to the right, and we'll go from there. So I'm going to put, we're doing V1, I don't know, whichever, just remember which order you put your coefficients in. So if we want to do V0, V1, then when I pull the V0 terms over, I have a negative 1 over 20. That becomes a positive 1 over 20. Right, so this is all my coefficients. of V0. This term right here gives me 1 over 10, and it was a negative, and it moves to the left as a positive. And then there's nothing from this side, so that's it. Plus all the coefficients of V1, and I have negative 1 over negative J8, so that's a positive 1 over J8. From the right-hand side, the 1 over 20 gets subtracted, and the 1 over 10 gets subtracted. And that all equals my constant term, which is the 2 phase of 30 divided by negative J8, but that has to be added to the right side, which counteracts the minus sign. So I have 2 phase of 30 degrees divided by J8. Okay? That's my first equation. And that's okay. As long as I'm careful and I use these parentheses, when I put these into the matrix elements of MATLAB, it will solve those just fine, right? It'll condense them. All right, so let's do Kcl at V0. So now I'm looking at this point, and I say, well, currents in, that's this one, equal currents out, that's this one, because no current flows into the input, right? So I just have 2, V1 minus V0 over 10, 10K, right? Divided by, or sorry, equals V0 minus 0 over negative J4K. Again, the K's cancel out. I can collect my terms to the left-hand side. And so I'm going to have negative 1 over 10. And the negative J4K, when this gets added, becomes positive 1 over J4. And that's all times V0. And my V1 term is just 1 over 10K. So that's 1 over 10 times V1 equals, and I have no constants, so that's equals 0. So now I have 2 equations. This is my second. 2 unknowns. We can plug those into MATLAB and solve. Okay? Once I solve this, it's going to spit me out a little matrix with V0 and V1. V0 is the output voltage we're looking for. But then I'm also looking for I0. So how do I find I0? Once I know V0 and V1. Yeah, right? It's just V1 minus V0 over 20K. So once you've found the 2 voltages, the current is pretty simple.
Wait, could you repeat that?
To find I0,
Yeah.
V1 minus V0 divided by 20. All right, so I don't want to have to pull up MATLAB just to plug that in. I think you guys can all do that one, right? Again, though, when you're doing these in MATLAB, be really, really careful, right? Don't be stingy with your parentheses. They're cheap, right? Put extra parentheses around every single denominator, okay? Anything that has like the J4s or whatever, just put parentheses around the denominators. Don't forget your parentheses around the main coefficients either, right? Because if I were typing this in and I didn't put a coefficient, you know, it might understand it without the parentheses. If I were careful in how I wrote this, you know, again, this is going to be a 1 over 20 plus 1 over 10. You know, I might even want to put parentheses around these. And as long as there's no spaces between them, it might catch it all as a single matrix element. But if you put one space in there, it's going to think that you've moved to the next element in that row, and you're going to confuse it. So just put the whole thing in parentheses. And then if you're not sure, you can always demarcate your one element from the next with a comma, if you have to, right? But again, as long as everything's in parentheses and then you do a space, MATLAB will interpret it all just fine. It's also always worth looking at, the output matrix. Make sure that in this case it's 4 elements in the matrix. If it gives you a 3×2 or something like that, something went wrong. That's why I don't usually, for these smaller matrices, I make sure I don't put a semicolon on the end of the line. That way I can see the output directly. Just kind of check myself. Any other questions about this one? your approach. You know? This was similar to number 11. In number 11, you didn't have VS defined though, and it was asking you for the input impedance of this circuit. So in that case, you're going to go through basically this exact same thing. Like I said, I think the layout of the circuit was almost identical. And you're going to find VO as a function of VS, right? And then you can find when you know the VO as a function of VS, you can also then solve wherever they define. They were defining the current out here. You could then solve for that current as well as a function of VS, and then you could plug it in, and that would cancel out the VS's. When you did the VO divided by IS, or the VS divided by IS, it gave you CS, right? And so once you divided by the IS with that unknown VS in it, the VS's will fall out, and then you'll get left with just an impedance. A few more steps again. But the solution of the op-amp circuit followed very similar technique. And that's a good approach for almost any op-amp circuit that you look at, not just this one, right? Again, it won't be very helpful because you were lucky 2 problems look the same, but again, most of the time they're not ever going to look the same again, right? So remembering to do KCL at the nodes, you know, applying your golden rule that the inputs are equal, applying KCL at the nodes, at those unknown nodes, that's the best approach that I can think of. It's also kind of handy when you're doing op-amps. You pretty much always need to do KCL at the input node. That one's pretty important, right? Even though you know it, right? That's one of the nodes you need to use, almost always.